Boa tarde a todas e a todos. É com grande prazer que estamos recebendo nessa Open Lecture da School of Advanced Studies on Water and Society Under Change, promovida pela CAPES e executada pela Escola de Engenharia de São Carlos, USP, junto com a Universidade Federal de Campina Grande e a Universidade Federal de Pernambuco. Tá? Nesse segundo módulo, nesse mês de abril, final de abril, início de maio, nós temos como tema central os grandes desafios do saneamento. E eu queria convidar, com grato prazer, para estar junto conosco, e um aplauso ao professor Nicholas Peter Hankins, da Universidade de Oxford. Seja bem-vindo. Please. Professor Nick Hankins. Please. Pode sentar aqui. Professor Nick Hankins is a frequent visiting professor of our graduate program, the graduate program of Water, Hydraulic and Sanitary Engineering of Escola de Engenharia de São Carlos, Universidade de São Paulo. Professor Nick Hankins has a long tradition and experience in related to different topics of sanitation, also with cleaning and treatment waters, but including aspects of challenging and innovation. The second person I like to invite here, and she's just here, is Marina Battaglini de Macedo. I would like to give her an applause also, because she is representing all the academia, all the students making a co-management of this school, and without the students, that will be unachievable, impossible. So thank you very much, Marina, for visiting us. Come together. So my words are very, very few. On behalf of the director of the School of Engineering, we are very proud that you, Nick, are here. Also, Professor Eduardo Cleto Pires, a senior professor of our department, is coming to this classroom, and also he is supporting for more projects, medium-term and long-term projects with University of Oxford. That means that all the department and the graduate program is working with synergies to promote the exchange of students, scholars in both sides, from Oxford to USP and from USP to Oxford, and also promoting other Brazilian scholars and other Brazilian early career students to profit of this channel of exchange experience, also looking for new funding opportunities in terms of scholarships, in terms of companies, water companies, working for a better future. Especially in this week, we have a full agenda until next Friday morning, when we are hosting a workshop with University of Oxford and other universities, University of Warwick, through video conference from the United Kingdom, University of Texas, San Antonio, and the SAAE, that is the São Carlos Water Facility, the water company. The International Institute of Ecology also was invited, and the Fundação FioCruz, related to tropical and subtropical disease, relating health, water, and resilience. For that reason, we hope you are going to enjoy this moment, and hoping that also, Nick, enjoy and shape with us a very, very fruitful future at the medium and the long term. So thank you, Nick, for coming. Okay?
Thank you,
like
Mario.
to put some words? Okay. Okay.
You can pass through one day, okay?
Okay.
And I think you also have a pointer here.
Okay. Well, let's just wait for the screen to warm up. So thanks again for all of you coming. Just want to say what a great pleasure it is to be invited to this workshop and to be part of this collaboration with USP. We don't hear a great deal about Brazilian universities outside in the UK, but we do hear about USP. It's known for its excellence, so I'm proud to be a part of this collaboration. And I'd like to thank Mario, who very capably organized this meeting, and Eduardo Clito Perez. And it's a great pleasure to be here. So what I'm going to do now then is to talk about a topic on clean water, and I'm going to try and relate that to the water, energy, and food nexus. And you know that I'm interested in sustainability, so I think many of you were here this morning. You may find there's some overlap with some of the things I discussed, but at least it's always good to hear things again so that you don't forget them. So I'm going to talk about clean water and the water, energy, food nexus and how to ensure a sustainable supply. So really this is a reflection both of my research and my vision or my ideas about some of the future directions that should be in this research area. But of course, other people may have different ideas. So I'm happy to hear your opinions as well. So in the talk, first of all, I'm going to introduce the Sustainability Nexus, and then I'm going to talk about the challenges, particularly of the water and energy and food nexus, because I think that you can't discuss these topics in isolation. They're all connected. So if we think about water, we have to think about energy. And if we think about water and energy, we have to think about food. And the three come together because they're the three most essential elements of life on Earth as we know it. And without them, we can't survive. And unfortunately, there's a monster that lives in the middle of all three, and we call that global climate change. And it's starting to affect all of us. So we have to think about this very carefully. I'm going to talk about my vision of some of the research challenges, particularly with reference to water reuse and desalination. So those are the two areas of my research. I'll talk particularly about water reuse because I think that's more relevant to your interests, but I think that desalination is going to be a topic of increasing importance in Brazil as well in the future. You have plenty of rain here, but you also have a lot of people living very near to the sea. And sea is an obvious source for water. And finally, I'll talk a little bit about the future directions and the conclusions. So I'm going to remind you again of the Brundtland report, which was published in 1987, where Mr. Brundtland said that sustainable development is development that meets the needs of the present generation without compromising the ability of future generations to meet their own needs. So that means that we have to do things that are good not just for us, but for our children and our grandchildren. We have to think towards the future. And I believe that sustainability should be an integral part of all engineering education. We know how to design things, but we need to know how to design them in a sustainable way. So that's a very important thing. The report concludes several things related to international cooperation, and I'm glad to see that we're all here today, people from Paraguay, from originally Argentina, the UK, Brazil, maybe some other countries. We have to work together because these problems are global. They're not local, they're not even national, they're worldwide. We need to improve the quality of life for the current global population, but also for future generations. And this idea of intergenerational equity, being fair not just to ourselves, but to our descendants. And basically, we have to live within the carrying capacity of the planet. We can't carry on as we are, because if we do, we'll have to move to other planets. And I just read the book by Stephen Hawking, who sadly died last year. And if you read the last chapter in his last book, he's saying that his belief is the only way we can survive as a human race is to move to other solar systems. And it's a very difficult ambition, but maybe that's where we're headed. Now, the sustainability nexus really lies at the intersection of three circles on the Venn diagram. We generally, as engineers, think about efficiency, about how well we can turn resources into products using a minimum amount of cost and labor and so on. And we're very good at doing that as engineers. We've been doing it for 200 years. But what we've been not so good at is thinking about the effect that that has on the environment. And not only the environment, but the effect it has on society. So the three E's are the efficiency, the environment, and the equity. So the social equity, how fair it is across society. And you can see that trying to meet a target, which is the intersection of these three circles, is a lot more difficult because it's a much smaller area. So you can see that indeed creating a sustainable solution is going to be a very difficult challenge. Sometimes we can design projects, processes, and systems where the three come together, and that's really what we want to do ideally, but the reality is that they fall apart because these are all driven by different groups. So the economics is driven by the companies and the manufacturers or the producers. The environment is either in control of nature itself or environmental groups, and then society is in the control of the government. But unfortunately, those three may not overlap, but they should do. And I told many of you this morning about how we measure this in terms of sustainability metrics. So there is a quantifiable way in which we can work out how well we've either done this or done this. And that's the role of sustainability metrics. Now, someone asked me a very good question this morning, is it really possible to invent a process that has zero waste? And I think the answer is no, it's impossible, but I can explain why. So those of you who may have studied thermodynamics, I'm not sure if that's part of your course, but the second law of thermodynamics tells me that if I have a small heat engine, I can put in some heat, I can put in some high quality energy, and I will do some work. So this is like a car engine. You burn gasoline or ethanol, you create high quality heat at high temperature. That drives the pistons in the engine, and that does work. But unfortunately, your engine gets very hot. It produces waste heat. In the same way, if you go for a run, you sweat a lot because your body burns calories, it creates energy for you to run, but you also warm up. And unfortunately, the second law of thermodynamics tells me that this is always a finite quantity. We cannot eliminate this. There may be ways to reduce it, but we can never completely eliminate it. And in the same way, you can think about sustainable processes in the same way, that what we're doing is turning precious resources, that may be raw water, or it may be raw energy, into something of value to society in terms of wealth, but also in terms of waste. And the efficiency can be measured in terms of the ratio of the wealth we create. I don't just mean money, I mean quality of life, general wealth, to the resources. So I think these two are comparable, and it really means that there is a constraint to how well we can do these, but we know that we can design more efficient car engines and more efficient jet engines. Why can't we invent more efficient processes and systems that allow us to create valuable benefits from the resources that we consume? So I think that's another thing to bear in mind. Remind you again of the challenges of the water, energy, food nexus. We know that many people in the world, that's about 1 in 6 of the population, have no access to safe or clean water. And an even bigger number have no access to proper treatment of their wastewater or sanitation. And that means a very large number of deaths per year related to either poor water, poor hygiene, or poor sanitation. So this is the kind of clean water nexus. And most of those people are children under the age of 5. And even in developed countries like the UK or in Brazil, people are affected by water poverty. Now, more seriously, water shortages will limit growth in the future. So it's going to limit economic growth. You can't have industry without water, and you can't have food without water. So this is going to have an effect on development. 97% of the world's fresh water is not fresh. It's saline and it's in the ocean. And it looks as if the ocean may, in the short term or medium term, be the only solution to our problems through desalination, especially when you consider that the largest or fastest growing cities are within 100 kilometers of the coast, and the nearest example of this is just a couple of 100 kilometers away. I don't have to tell you. So certainly there's a problem here with water availability, and we have to solve it. We need new technologies to do this in a sustainable way. So the Water Poverty Index is a way in which we can measure the poverty of the society with respect to water, which is a composite index which takes into account the resources available in terms of surface water and groundwater. We can think about the access that people have both to clean and safe water, to sanitation and to irrigation for agriculture. So that's another factor. We can also think about capacity. So remember that capacity is the ability of people to use the technology, either in terms of income to purchase equipment or access to education to use that type of equipment. It's not obvious to everybody how to use the technology, or even through lobbying in the political establishment, which is empowerment. So all of those things have an effect on the capacity of the people to achieve water richness, if you like. And finally, we have the kind of use, the distribution of use, whether that's more domestic use for personal use or for agriculture or industry. And finally, the environment. So how good is the environment that the water is being discharged into? If you have very poor water treatment or poor sanitation, and you discharge that dirty water into an ecosystem, you're going to do more damage to it, and that will have a negative feedback effect on the society. So we have to think about the environment as well. All of those terms are now summed and weighted, and that gives us a water poverty index. And again, here's the bad news, or this is the current picture. You can see the water poverty index is color-coded from blue, where it's low, through ochre, which is sort of orange, to yellow and green, and finally to red. And what stands out most markedly is the region of Africa and the Middle East. So you see that pretty much most of those countries are either green or red below the Saharan Desert, the Kalahari Desert, and so on. And then the Middle East moving out towards the Far East, so India in South Asia, China, Mongolia, Nepal, and some other countries. So you can see that there's a serious problem in this part of the world. Here in Brazil, there is still some medium problems. So I guess you have a lot of rainfall, but you don't always have access to the treatment of that water for use. Whereas the north of Europe and Canada, and it seems as if you're near to the north, you're better off. But certainly there's a serious problem there. And again, you can relate water poverty to general quality of lifestyle. So those countries that have a high life expectancy at birth, that have a high human index or human development index, also have a very high water richness. So remember, this number increases for the lower poverty. And you see that at the top, Norway and the UK figure quite highly, and then you drop through China, Russia, China, which has been increasing actually in the last few years, and down to the sub-Saharan country of Niger, where there's a very low life expectancy and a very poor water poverty index. So as might be expected, there's a correlation between the two. And that means that really water is a reflection of the quality of life in general, but it's also a reflection of the access of people to the water, food, and energy nexus, because when that is working well, it works well for each one of the three corners of that triangle. And I think that's something to bear in mind. We can't think about water in isolation. We have to think about it in connection with food and with water. So how does that work? Well, we have a kind of triangle here, and at each vertex of the triangle I have one of the three main resources. We have clean water, we have energy, and we have food. And each one of these vertices is interconnected. So as an example, if I want to generate energy using a conventional power station, I need water, because I need water to cool the system and to generate steam in the turbines which run the generators. So you need a lot of water to generate power. And we'll see later, actually, you need even more to generate nuclear power. I believe you still have a nuclear power station in Angara dos Reis. I don't know if that's still working, but it uses a lot of water. At the same time, we need energy to create water. We need energy to treat the water or to desalinate it or to treat the wastewater. So those two are linked. On this side, we need energy to grow food, mostly solar energy or heat in a greenhouse, or to process it or transport it. So there's a lot of embodied energy that's required to produce food. Food, on the other hand, can be used to generate energy. Huge industry in this country for biofuels, like sugarcane, and in the US they grow corn to produce energy. So those two are linked. And on this side, obviously we need huge amounts of water to produce food. In fact, food production, agriculture, is probably the biggest consumer of water. Of all uses, it's about 70%. It's very large. But in the same way, food is a vital source of water for many animals in the desert. So camels can eat things that contain water and keep them going for a long time, or they can eat things that store water. So all of these things are connected, and there's a monster in the middle, as I mentioned, that's climate change. Climate change is going to affect the availability of water because of flood events or because of dry events. It's going to affect climate change is possibly caused by energy production, especially carbon fuel use, producing CO2 and greenhouse gases. And obviously, climate change will affect the ability to grow food, because if it's too hot or too dry, we can't do that anymore. And you see extreme weather events already affecting food production in certain countries. So there's been problems, I think, in Canada to produce wheat in recent years. So all of these things are connected, and what I'm saying, my idea is that you cannot consider these in isolation, and I'm going to give you now some examples in a minute about that. Let's just have a look at water-stressed countries. So these are the most water-stressed countries in the world. All of these are in the Arabian Peninsula, as it happens, so, and North Africa. So what I've done here is to plot a country against the consumption of water per day. And then I've calculated that as a percentage of their renewable resources. So how much water do they consume divided by how much is actually available in a renewable way, in other words, from surface water or groundwater for those people. And at the top of the list is United Arab Emirates, which is consuming 1,200% of its available water resources. And the list goes on. Kuwait is 1,000%, Libya, Saudi Arabia. We drop down to countries like Egypt, and then Israel is 78%. Tunisia is 50%. All of these countries are using more than 40% of their renewable water for irrigation. So that explains why these numbers are very high, because all of these countries try to grow crops really in places where it's very difficult to grow crops. And so they have to use a lot of non-renewable water for irrigation. And that water mainly comes from desalination. So this is a very non-sustainable practice. Extreme proportions indicate reliance upon non-renewable resources. And this is where we're all headed because of climate change if we don't do something about it. We have a very serious problem of overuse of water, and it's simply not sustainable. So clearly we have a mismatch between the water and food in the nexus. Let's have a look at some other examples, the interaction of water with energy. So this is a diagram that gives you pictorially an example of how much water we use to generate electricity. So in a combined gas and steam cycle to generate electricity, we consume between 7,000 and 20,000 gallons of water to produce 1 megawatt hour of electricity. A megawatt hour means a megawatt for an hour. Typical power station produces maybe a gigawatt, and it's running constantly. So you can do the mathematics. You realize that power stations use awfully large amounts of water. And it increases if you have a power station fired by coal and oil. and even higher if you have a nuclear power station. So people say, well, let's switch to nuclear power because it's safe. Well, debatable. Let's go to nuclear power because it's non-carbon. It doesn't produce greenhouse gases, but look at how much water it uses. So you do well for energy, but you do very badly for water. Let's look at the energy that's required to generate water. So that's the other side of the wall, if you like. How much energy do I need to create water? If I simply take water out of a lake or a river and purify it, so I have to treat it to remove organic matter, to remove colloids, to remove bacteria, I need about 1,400 kilowatt hours, so about 1.4 megawatt hours. So remember, that's how much water I need to generate that much amount of million gallons. You can compare the two and you can see that, in fact, quite a lot of the water is needed to generate the water, and that doesn't look very sustainable either. Groundwater, slightly higher. The groundwater is often saline, so it needs to be desalinated. The interesting thing is that if we recycle wastewater, it doesn't require a lot more energy than it does to purify the surface water. So for about double the energy, we can actually recycle our wastewater. And that means that wastewater treatment should be a very attractive proposition. It's something that we really need to think about because it offers at least a medium-term solution to a water crisis. If we're really desperate, we can go to seawater and desalinate that. But with the current technology, we need about 10,000 kilowatt hours to produce 1 million gallons. So 10 megawatt hours will be 10 times the amount of water here to produce 1 million gallons. So again, you can see that you need almost as much water to generate the water from desalination as you gain from it. And that means that really we can't be using conventional energy generation to produce water. We need to use renewable energies. We need to use solar power. We need to use wind power, geothermal energy to generate this electricity directly without the use of so much water. Let's look at an example maybe a bit closer to home for you, which is the use of biofuels. So we can say, well, let's go from gasoline vehicles to ethanol vehicles or hydrogen fuel cell vehicles or maybe even hybrids. So there's quite a lot of, I've noticed here in Brazil, there's quite a few hybrid vehicles now, not so much Tesla. There's a new model, I think, by Toyota, I forget the company, but the idea is that you can either plug them in or when you're putting your brakes in the car, that's generating electricity to power up the battery. The point is that by using these kinds of fuels, you can reduce the carbon impact, the production of greenhouse gases. But in order to run them, you need water. So even to produce gasoline, I showed you a picture this morning of a refinery, you need lots of water to run refineries. So you have that amount of water. If you go into a plug-in hybrid vehicle, you need a lot more water because of processing the energy source. Hydrogen fuel cells need water to operate, so that's even higher. But look at this. For an ethanol vehicle, you need 100 times the amount of water. And that's simply because we have to grow the sugarcane. So the sugarcane needs a lot of irrigation. So if you think that biofuels is going to answer the climate change problem, it may well do, but it's not going to answer the water problem. Now, I discussed this with Professor Eduardo this morning, and he shrugged his shoulders and said, well, actually, where we grow it in Sao Paulo, we have plenty of rain. It's not a problem. But we can't do this worldwide. We don't have this amount of water worldwide. So you see how we get into this problem where we solve one problem in the nexus, but we create another one. And I think that's a very difficult challenge to solve them all simultaneously. But that's really the way forward. So the first part of my lecture, then, I hope what I've convinced you of is the fact that clean water provision needs to be integrated well within the, oops, sorry, I've pushed too many buttons, I'll go back. It should be integrated within the water and energy and food nexus. And it's also obvious, I hope it's obvious to common sense, that if we're short of water, the answer is not just to build new reservoirs. You have a lot of reservoirs in Sao Paulo state, I think, on the Tietê River, on the Paraná River, I've seen quite a few of them. You can't drill new wells into the earth. You can't build pipelines to transfer water over very large distances because all of these things require huge amounts of resources and huge amounts of energy, and they're just not sustainable. So what we need is novel or improved sustainable technologies which are efficient both in terms of energy and chemical use, and importantly have a low cost, a low footprint in terms of the environment, in terms of carbon footprint and climate change, and they are urgently needed for water reuse and desalination. So here's a challenge I'm going to throw to you. This is what we need to solve, the problem of how are we going to reuse our water, or how are we going to desalinate it, but we're going to do it in a sustainable way that sits comfortably within the WEF nexus. And I hope that powering through renewable energy and using membrane processes and using nanotechnology will play an important role. I just want to make a few more points about wastewater treatment, and these are ones that are quite important now in Europe. So the emphasis in wastewater treatment now is on reducing waste, on reclaiming valuable resources and recycling those resources. So we have water that we can recycle, but we also have in the wastewater raw materials like metals, I explained this morning, and embodied energy, so you have organics that can be converted into methane, which can be used as a kind of renewable energy source. So wastewater is not wastewater, it's a resource. It's a resource that should be one, so don't use the word waste. We have a saying in English, waste not, want not. You mustn't waste it, think about it as a resource. Here are some of the problems that are coming on to the horizon in Europe and the UK, and I believe here too, and it's how we remove emerging microcontaminants, things that are present in very small concentrations but cannot be removed by conventional processes like activated sludge. They include disinfection byproducts that are caused by chlorination of the organics in the wastewater, endocrine disrupting compounds that are derived really from human female hormones like estrogen, and then we have trace heavy metals, pharmaceutically active compounds, things like ibuprofen or beta blockers used to treat heart disease. They're all appearing in wastewater, and they have to be removed or they're going to have an effect on the local environment. So that's a very serious problem now in Europe. Another point I'd like to make is that membrane bioreactors, there's a future for this because they're competing very well now with conventional activated sludge. We've had this for more than 100 years with very few improvements, but really it can be improved using membrane bioreactors. And it will provide a potable filtrate of better quality than tertiary treated effluent, so very low turbidity and very low TOC. So really, the water we can recycle using a membrane reactor can be very good. Now, a few sort of statements of what's happening in the world. It's estimated that by 2030, there'll be a global water shortfall of about 2,700 billion cubic meters of water. Now, just as a calculation, if supposing that we were going to generate that amount of water through desalination, which may be where we're headed, fossil fuel desalination would consume something like 770 gigawatts constantly, creating CO2 emissions, and I did the calculation of 3.4 gigatons a year, and that's 10% of global emissions. So by trying to fill the water shortfall using desalination, we're going to create 10% of global emissions. So this is clearly not sustainable. And that really brings me back to the idea that we have to think not just about desalination, but wastewater treatment. We have to use less and do more with it. So membrane technology membrane separation technology and nanotechnology are certainly on the increase. So to give you an idea, there's an increase. They're increasing annually, the products and services associated with membranes. So the market by next year is expected to be about $52 billion US, and that's risen by 320% from just 10 years ago. And you'll see that 50% of the market for that is in the Middle East and North Africa, not surprisingly. But the market for reverse osmosis alone, which is used both for desalination and wastewater, is going to reach 40 billion. So if you're a speculator on the stock market, you should invest in membrane technology because you're going to make a lot of money. So I'm going to talk a little bit about membranes and nanotechnology. So membranes, we've said that there's a growing market, not just for water, but for other applications. But 50% is actually in the water sector alone. And global demand's increasing by about 9% annually to this kind of figure. Membrane modification technologies I'm going to talk about later are being used to improve the efficiency and performance of the membrane. We can also think about nanotechnology. So you've all heard about nanoparticles, nanostructures, and so on. They're also playing a fundamental role in technological innovation. And playing very good roles now in monitoring of the environment and for water purification, for things like filtration, detoxification, certainly in desalination. So these two areas, I think, are of rapidly growing importance, whether you like it or not. And this is really where a lot of time and energy needs to be devoted if we're going to develop these new and sustainable technologies. Now, there may be other technologies, bioreactor technologies, which I'm not expert in. So I'm not saying that this is the be-all and end-all. It's not the whole story, but it's an important part of it. So let me explain to you a little bit about what membranes are. So a membrane is really a separation between two phases. It's a very thin sheet. It's an interface separating two phases which selectively controls the transfer between the two phases. So in other words, supposing I have a membrane which contains different kinds of particles. Some of the particles will be rejected and some of them will move through. And the size of particle that moves through will depend on the kind of membrane I have. So if I start with what we call a microfiltration membrane will reject anything except, it will allow anything to move through it apart from fairly large particles of the order of 1 micron. An ultrafiltration will reject both the particles and macromolecules, so things like polymers or sugars or proteins. A nanofiltration will reject things like acids, divalent salts and sugars, but it will allow the other things to move through. The tightest membrane we have is reverse osmosis, which will reject everything, including monovalent salts and so on, but it will allow the water to move through. So by selectively changing the pore size in the membrane, I can selectively control what moves through. And it turns out that it's particularly useful for materials which are of biological, organic, or inorganic origin. And guess what? Most contaminants in wastewater are one of these three, so it's obviously a very good choice. And better still, they can be run at ambient temperatures, so they can be run at 20 or 25 degrees. They have a relatively low cost. They can be built in modules, so we can build them like Lego, put them together, and they are highly effective and energy efficient. So here's an example of how membranes are taking over the world. So on the left, I have a list of all the conventional water treatment technologies. Things like coagulation and flocculation to remove colloids, or sand filtration to remove bacteria and other things. Chemical treatments, activated carbon for adsorption. UV treatment, that will destroy, oxidize organics. Biological treatment does the same. Ion exchange, I mentioned this morning. Deionization, and even distillation. So those are all conventional treatments, but they can all be replaced by equivalent processes using membranes, whether that's a microfiltration or nano, an ultra, or reverse osmosis. And we can do more. We can make special kinds of membranes. We can make them nanocomposite, or we can make them responsive. So that means that we can give them the ability to give us advanced reduction and oxidation all in one place. We don't need all those processes together. We can just do one single membrane and do all of these. Oxidation, adsorption, metal capturing. We can place functional groups to do chemistry on the membrane. And we can also put in artificial channels. We can enhance the flux, the water flux, and we can have anti-fouling to stop them from the surface from getting fouled up. So water treatment strategies used in industry, those are the solid lines, and these are emerging applications as we develop new kinds of membranes. But there's only so far we can go, actually, with any kind of water treatment process. And that's because we have a thermodynamic energy limit. So there's a minimum energy that will be required to treat and clean up a water stream. And it turns out that if we calculate this minimum energy, it gives us a benchmark against which to compare processes. So how do we calculate this? Well, we need to use a little bit of thermodynamics. and the first and second law. And what we do is calculate the energy of mixing. So if we have a clean water, we mix that with contaminants, we'll get an energy of mixing. And the work that's required to purify that stream is exactly equal and opposite in size, because we're using a reversible process. And that's related to the free energy of mixing. So we can actually calculate it from the osmotic pressure and the volume. And then what we can do is calculate how much that energy will be as a function of both the recovery, so the amount of water that we claim, but also the concentration of the salt or solute that's in that solution. And you can see that as the recovery increases, obviously the energy increases, but as I go from a dilute solution to a more concentrated one, I need more energy as well. So this is where we are right now, 50% recovery of a solution which contains about 25 or 35 grams a litre, which is equivalent to seawater. You need about roughly 1.1 kilowatt hours per cubic metre. Now this graph on the right explains how the requirement for energy has dropped over the years. So in the 1970s, we were using 15 kilowatt hours per cubic metre to carry out that water treatment, and it's dropped exponentially, but it's reaching a limit. This dotted line is the thermodynamic limit, and we're actually only about twice of that limit. So there's not much further we can go. I've amplified it there. You can see that we're getting very close to that line. So we're doing very well, and that means that we've kind of reached an asymptote that we can't go beyond. So what do? We've got an almost perfect machine now to desalinate things, but there must be a way forward. Well, we've created energy-saving devices in things like reverse osmosis, where we can do energy recycling. So in this device, what happens is you pressurize the seawater to move through the membrane, and some of the energy associated with the rejected water can be used to increase pressure back into the feed water. So this is a way in which we recycle water. You've also probably heard about new kinds of membranes, things like graphene sheets that are being used for desalination, or for carbon nanotubes. That's another area. And in these types of membrane, you can have an almost perfect separation of water. So the water will move through the carbon nanotube, but the salt gets trapped. So these are kind of almost biomimetic. They mimic nature, and they're becoming very, very efficient. But that means that we're getting very close to the limit of what we can do. So as we approach the thermodynamic limit, having high permeability membranes is not going to reduce the cost of the reverse osmosis, because you can calculate the energy we require and the excess energy for pumping. What we're going to find is that the pumping energy is very close to the osmotic pressure, because that means that we're operating almost reversibly, and there's very little difference between the two. But it also, if we can create membranes that allow higher fluxes, the beauty of that is that we can have smaller modules. So if we have smaller modules, that means we have smaller plant, and that reduces the cost of the plant. So it's not so much about the energy of running the operation as the cost of building the plant in the first place, and that means we can save a lot in size. So I believe that there's not much future now for making very, very nice membranes, because we're already getting near to that already. But it will mean that we can build plants more cheaply, and I think that's important. But there's other things we can do with membranes. We can make them smart. We can make them do things we want to do. This picture's not very clear, but we can make membranes in two ways. We can cast them into flat sheets, or we can spin them into hollow fibers. But either way, we can change the surface properties. We can make them hydrophilic, we can give them charges, we can give them functional groups, and that means that we can make them antibacterial, we can make them photocatalytic, we can make them adsorptive, and that means they'll have special properties. Now here's an example. I can have a polymer which has functional groups here. These groups become protonated at low pH, but at high pH they lose their protons, and therefore the repulsion decreases, and you see how that collapses. So what that means is, if I have a polymer like this which collapses, the permeability here becomes higher because the water can move through, whereas here it's getting trapped. So by changing the pH, I can change the permeability. So the permeability of the membrane will respond to the pH of the fluid that's going through it. And this can be done using different kinds of nanocomposites of membrane. So we have the ability to make smart membranes, and that means that there's a lot of future for new kinds of devices we can make with the membranes to respond in a smart way to the fluids that they're supposed to treat. I mentioned renewable energy. I think that there's going to be a future in the use of renewable energy to drive membranes for precisely the reasons I said before, that we can't use electrically generated energy. It's just not sustainable. But there are lots of examples of renewable energy. We can get it straight from the sun using photovoltaic cells to generate electrical power. But we can also use solar energy to generate biofuels, as we know. So there's a source of primary source of renewable energy. Secondary source, because when the sun shines, ultimately it creates wind. The movement of the wind creates waves. The movement of the moon creates tides. We also have geothermal energy deep within the earth. And finally, don't forget, we have a lot of waste energy that's coming out of industry. So power stations generate a lot of waste energy, and that's a resource in itself. And I'll show you in a minute how that might be used in a device. But here I've just given you an example of desalination processes that are being used to desalinate water. Here we have reverse osmosis that's being used with energy recovery to generate clean water. So I think renewable energy is going to play an important part in membrane water treatment. Okay. Now, I'll talk very briefly about nanotechnology, just because of time limitations. So there's lots of applications now for nanotechnology in all of these different kinds of systems. As an example here, I have a particle which contains some antimicrobial agents. It also contains these recognition agents. So what the recognition agent does is it's able to target itself onto a receptor on a microbe. So this microbe, it's something that we want to get rid of. This thing sort of fits into the slot there, and once it fits in, it will release its deadly charge of antimicrobial and it will kill the bacteria. Here's some more examples where I have a core and shell. So I have a magnetic core that's surrounded by a silica coating, and I can functionalize that shell using antimicrobial agents, or I can use adsorbents, or I can use photocatalysts, and all of these can be used in different ways to treat the water. So applications in new kinds of absorbents, in new kinds of disinfection and microbe control, the removal of problematic ions like phosphate and chromium. We have doped titanium photocatalysts for oxidation. We have nanocomposite membranes I've just mentioned, and even nanosensors which can target and pick out particular sort of compounds. So a lot of active research going on in this area. I've quoted a very good review paper of that. It's well worth reading if you have the time. So a lot of promise in nanotechnology as well. Now I'll bring the two together and talk about one of my particular research interests, which is forward osmosis. So there was a report in National Geographic magazine not too long ago which said that forward osmosis was one of the 3 technologies that promised to reduce the energy requirements of water reuse and desalination by up to 30%. And if you go to the literature and study the output of articles on forward osmosis, you'll find that the number of articles that have been published has increased very sharply in the last 10 years. So there's been an exponential increase, and it's about to level off, but there's about 200 or 300 publications every year in that subject alone. So that's one paper every day just on forward osmosis. What are the other technologies? Well, I mentioned the carbon nanotubes. So here you have a membrane that's made by fixing the carbon nanotubes into a kind of sheet, and you can see that water moves through almost unhindered. It moves through that tube without any problem at all, but the charge groups get trapped. So carbon nanotubes are good to make membranes. The only problem is that the biggest membrane we ever made was about a square millimeter, which is not practical. We need to have much bigger membranes. If you're running a membrane plant that's treating 1 million cubic meters a day, which you might have in a big city, it's not going to work. And then we also have biomimetic membranes that mimic what goes on in nature. So you can have very clever membranes that not only can trap charges, but they can allow or prevent proteins from moving through. So this is what's going on in each membrane in the cells in your body. It's allowing water to move through, sometimes allows proteins to move through, and it's trapping salts. So we can actually copy nature when we do that. Let me talk a little bit more then about forward osmosis. Again, I'm repeating this for some of you. So in forward osmosis, what happens is we have two solutions. We have a feed solution that we'd like to treat, and we have a draw solution which is going to pull that water out under osmotic pressure. And between the two, we have a semi-permeable membrane which will reject the salt but allow the water to move through. So I start off with my saline feed water. That may be wastewater, or it may be seawater. On the other side, I have this thing called the draw solution, which is an idealized solution that's concentrated, but it contains a solute that I can easily remove. And I can easily remove it just by changing its temperature, or by using a magnet, or by using some other thing. But the point is, this has a very high osmotic pressure. And what's going to do is it's going to draw this water out into here. So let's see that happen. So you see how the water's been drawn from the left hand to the right hand through this semi-permeable salt-rejecting membrane. And that means now all I need to do is to remove this solute, and I can recover the clean water. And that I can do using cheap resources. I can use waste heat. So I'm going to put this all together and make a device that can be used both to treat wastewater and to recover the clean water from it. So I'm going to create a thing called an FO membrane reactor. And in brackets, I have a thing called an MD, which is a membrane distillation. I'll explain how that works in a minute. But the point is, here you have a membrane inserted into a biotank. So you have a biological process that's going on that's creating sludge. And the water within this tank's been drawn out by this draw solution. So this means that the organics become more concentrated and they can react more rapidly. But the clean water is being drawn out into the draw solution. All I have to do now is to use some waste heat to generate the clean water. And to do that, I can use fairly low temperature heat. I can use the heat from the back of a condenser in a power station, which is about 40 degrees, or I can even use solar heat. So I can do all of that without applying a hydraulic pressure. I don't need to use very much air to clean the membrane. I have a dense membrane which rejects all of the solids and even retains organics. So I have a very high organic retention time, which improves the productivity. But it also means that the water that comes out has a very, very low dissolved organic concentration. So it's very, very clean, much less than you'd have for conventional bioreactors. And it also allows us to remove some of those problematic microcontaminants I mentioned to you earlier. So now I'm just going to concentrate a little bit on this device using a thing called membrane distillation, which some of you may not have heard of. Let me explain what it is. In essence, what you have is you have a membrane in which you have two streams on either side. You have a hot stream here, a hot feed, and you have a cold permeate. So what happens is this membrane is very hydrophobic. It won't allow water to move through, but it will allow water vapor to move through. So this hot feed has quite a high water vapor pressure. The water vapor moves through the membrane. It reaches the cold side and condenses. And then the only difference in device is really a question of how we create that cooling effect. So in one case here, I have an air gap, and I use a cold surface that allows the liquid to condense, and I can collect it here. In this case, I use a cold sweeping gas, again, to collect the permeate. Or in this case, I just have a vacuum, and again, it will condense out into the vacuum. So here I have a liquid gap, and here this one is a cold sweeping gas and a condensing surface. So these ideas can be combined. But this is the basic idea. You have hot and cold, and the water vapor moves through. So if I have a salty solution or a draw solution here, I can recover the clean water on that side, and I can reconcentrate my draw solution there. Now, this all sounds very fun, and I was chatting to Professor Eduardo this morning. All fine and well if we can do it in the lab, but does this really work in the real world if we try to scale it up? And the answer is yes, it does, because it's used in Singapore. So Singapore is the country for recycled water right now, and they have a product called New Water. So New Water is essentially taking human wastewater and recycling it into potable water. So if you buy potable water bottles in Singapore, almost certainly that's passed through a human being, which is interesting because it's a total recycle. And the way it works is you have a conventional activated sludge process, which recovers about 90% of the water from the dirty water, but then you need to have a membrane process, a microfiltration, ultrafiltration, to remove some of the very large, nasty organic materials. And finally, you have a reverse osmosis to allow polishing. Now, that means across the process, you have a recovery of about 73%. So not bad. You know, we start with 100 units of wastewater. We recover 73 units of potable drinking water. We can improve on that if we combine a membrane bioreactor with an RO. So this is something that's ongoing now in Singapore. So the membrane bioreactor, rather like the CeTI-SC, will give you a high recovery, and then you apply a polishing step. In this case, we can recover slightly more, so we can take that up to 78%. But if you use an FO-MBR, you can have a very high recovery from the wastewater, and then if we apply MD or RO, as I just showed, to clean up the draw solution, you can achieve 94% recovery. So compare that to that, and that's using less energy than that. So there's a real future for this, this device. And indeed, there are people in Singapore who are actually working with me on this process. The only catch is that in the membrane tank, you need to have a biomass which is halo tolerant. So it has to deal with the higher salinities in the tank, but we know that it's easy to actually generate the right kind of colonies to do that. And we also need new kinds of membrane. But anyway, it does work. I think I'm going to skip this slide. This is really just electrodialysis. That's another emerging area of technology that's being used to desalination, using alternating electrodes to collect clean water and salty water in alternating compartments so that we can concentrate the salt and produce clean water on this side. I'll give you some examples of how we can introduce water treatment sustainably within the WEF nexus. There's an obvious one actually, which is where we're generating power near to desalination plants. So if you go to the Arabian Gulf, which I do very often, because I have a large project in the country of Bahrain. If you go there, you'll see that very often they have very large desalination plants on the coast which are near to power generation because you need the power to run the desalination plant. But it turns out that the brine concentrate that's produced by the desalination is pumped back into the sea, and that's very bad because it has a serious environmental problem. If you go to the Arabian Gulf, you'll see that there's very little alive in the sea there because it's so salinated now and because there's so much traffic moving through the sea anyway. But the brine can be diluted by using the cooling water from the power plant. So at least we can alleviate some of the problems on the environment by diluting it with the cooling water from the power plant itself. So that's one thing that's starting to go on. Here's another idea that I developed, which is where you combine the sequestration of carbon dioxide and capture with desalination by forward osmosis. So it really starts down here, where we have a saline aquifer, which contains salty water that we'd like to remove water from, but we need to do desalination. And on the surface here, I have a power plant that's generating carbon dioxide. I'm burning coal with oxygen to produce carbon dioxide. So what I do is I use calcium carbonate as a kind of adsorbent to remove the CO2. So calcium carbonate will dissolve in water at the right pH to produce calcium bicarbonate, and that actually acts as a draw solution. So we use that as a draw solution to remove water from the salty water down here, and that gives me a dilute draw solution. If I then use the waste heat from the power plant, I can regenerate the draw solution in the way I explained, and that creates clean water. Some of that clean water has to be used to dilute the draw solution, but some of it is clean water. So if you look at the overall material balance here, I'm putting in carbon, I'm extracting H2O, and I'm going to sequester my CO2 into the aquifer. So it doesn't get better than that. You're solving two problems at once. One is CO2 generation, and the other one is desalination. So we already made a patent on that, and we're in discussion with a company in Israel to develop it as a technology. Another one down here is what we call pressure retarded osmosis, which is where we can generate water and energy. So what we do is we use the forward osmosis in a kind of closed loop. So as the water is drawn into the draw solution, but we kind of trap the draw solution, and that increases the pressure. And then we decrease the pressure through a turbine to do work. And then we use a small distillation column here to regenerate the draw solution. So the draw solution is being recovered and concentrated to be sent back in here, and then the working fluid is sent back in here, and it's drawn back across the membrane to generate more power. So what I basically get is I get clean water and I get work coming out. So pressure retarded osmosis is another area of active research in Singapore. I'm getting to the end of the talk. I want to talk about ways in which we can actually hybridize desalination with wastewater treatment to actually run the system at low energy. So what I do is I start off with some wastewater, which is fairly low salinity, and I can treat that using a reverse osmosis process to give me clean water and brine. So this is the wastewater brine. So I've removed the organics, but I still have salt. Now I have clean water, and I have one volume of wastewater here, which is brine. And what I can do is I can use that as a kind of feed into another process where I'm using seawater as a draw solution. So what happens is one unit of seawater comes in, it's being diluted because it's the draw solution. The brine is the feed, and that's being concentrated, and that gives me a product here which can then be desalinated. And the thing is, this is more dilute than this. So when I dilute this solution, this seawater, I need less energy. So I can do seawater reverse osmosis, gain another unit of water there, and the brine that's being created can then be combined with the wastewater brine. And because those two have different concentrations, I can run a pressure retarded osmosis system to create more energy and some more diluted brine. So in other words, I start off with 4 units of wastewater, 1 unit of seawater, and I achieve 3 units of clean water, 1 unit of brine, 2 units of diluted brine, and a lot of energy. And we can actually look at the calculations. So if this is a conventional seawater reverse osmosis, I have to take the water in and pre-treat it. So even pre-treating the water takes about 0.3 kilowatt hours per cubic meter. I then run the RO plant, and I showed you the figures earlier. Even with energy recovery, I'm needing about 2.2 kilowatt hours, and then I do some post-treatment. So the energy balance turns out to be about 2.5 kilowatt hours per cubic meter. Now let's use a low energy hybrid process. The FO dilution, which is created by using the wastewater reverse osmosis brine, pays some energy back. The RO plant is running at diluted condition, so it requires less energy as well. And then by generating power from pressure retarded osmosis, I have some more energy as well. So add those together, and the total energy requirement is minus 0.8. Compare that to that. That's almost 3 times lower, or more than 3 times lower. So by combining wastewater treatment with desalination, which is something accessible to you here in Brazil, I think you can save a lot of energy. And the final idea, just very quickly, biofilm development. I mentioned this morning that biofouling is very bad for membranes, but there's clever things we can do with biology to try to reduce the development of biofilms in the first place. So bacteria attach, and it turns out that bacteria talk to each other through a thing called quorum sensing. They send out biochemical markers that say, hey, I'm here, come and join me, and then they all start growing together. And it takes a lot of dispersal to get rid of them. So what we can do is quorum quenching, where we try to suppress these biochemical signals to stop them from attracting each other in the first place. That reduces the biofilm development. So that's an area of active research, not my own, but it's going on right now as a way to mitigate the biofilm problems. Now, there's something that's... Okay, almost the final slide. This is a kind of osmotic battery. So this is a way in which we can use water treatment as a way to save or store renewable energy. A lot of researchers at the moment are looking on ways in which renewable energy can be stored. The problem is you can't store sunshine, you can't store wind, or you can't store wave. What you have to do is convert that into some other form of energy which can be stored. So a colleague of mine at Oxford who's been to this university many times, René Bonares Alcantara from Mexico, is looking at the generation of ammonia to do just that thing. But this is my idea, which is that you can basically have two reservoirs, one that contains very low salinity clean water and one which contains a lot of salinity. And when you have excess energy, you can run a plant which will separate the two. So you'll separate the salt from the water, and you can have clean water which can be used, and you'll have this concentrated raw reservoir. But in times where it's cloudy and it's not windy and there's no waves, then you can put this into reverse and you can run a pressure retarded osmosis plant to generate energy on demand. That means that you can go in both directions. So there may be some future with this as a way to store both renewable energy and to generate water. So the osmotic battery concept. And I should acknowledge my colleague in Singapore, Tony Fain, who was the guy who invented that idea. So do have a look at Tony's publications. His H index is something like 200, so he's a good guy. I was going to mention very quickly water as a finite resource, so we can recharge water back into aquifers. We should think about leak detection because lots of water gets lost in the distribution network where we have pipe works. Almost 50% of the water can actually leak away. And we need to have real-time monitoring for distribution systems. Okay, but I'll just try to wrap up. So I think in the future we need to invest in R&D to integrate sustainable or renewable energy with both water reuse and desalination. The key membrane areas for me are going to be in all of these membrane technologies. So I mentioned forward osmosis, electrodialysis, ultrafiltration, and of course the controlling of the fouling on the membranes. So in particular, we need new membranes and draw solutes for the forward osmosis. We need to do better with membrane distillation, so better membranes and modules. And also the issue of pretreatment so that we can actually reduce the energy consumption. And finally, I've mentioned groundwater reinjection as a way to store the water. I think we should think a lot more about community-based water treatment because a lot of places where people need money, water, are in very small villages or small communities, and it's not practical to build treatment plants 1,000 kilometers away. You need to apply it at source. So community-based systems are a way of thinking in their own right. And I imagine there must be someone in this department who's thinking about that right now. We also need international research collaboration. So in conclusion, I think future water shortfalls need to be addressed by sustainable, renewable systems for both wastewater reuse and desalination. So this is a key sort of message from my talk. But they should be integrated both within the WEF nexus and within the sustainability nexus. And I believe that renewable energy, membranes, and nanotechnology will play a key role. So thanks for your attention. Here's my new book. You'll find a lot of these things discussed in there. I put that in the reading list. I hope you have it in the library. If not, you should get some copies or order it. It's a very good... It's an edited book, really, so I wrote some of the chapters, but a lot of my colleagues wrote the other chapters. And finally, some pictures of Oxford. And I think now we're going to answer questions, right?
Wants to be the first, or should I do? Should I present first? Well, I will start then. Well, We talked this last afternoon about the limitations of biotreatment. And well, although I came a little bit late because we are preparing a program for an extended visit of Dr. Hankins for the second semester, and I was taking care of it. But I noticed some interesting interaction or use of both technologies, biological treatment plus, I would say, chemical and physical treatment. And I think that one message that from this talk is that we need to study a little bit more of these new technologies. Otherwise, we will be staying behind, definitely. And one thing that we need to introduce is courses on these new technologies. And my question, or something that Professor Hankins may add a little bit more, it's how you start doing this coupling of technologies, because usually we don't see this very often.
Thank you. So I think that's a very good point. Let me start really with the bioprocesses. We said earlier that bioprocesses have been around now for about 100 years, more than 100 years. The activated sludge was actually invented in Manchester, which is the city of my birth, and it hasn't changed at all in 100 years. And it's not even used universally. I think there's limited use even in Brazil. There are some cities that don't treat their wastewater, or smaller places, you know. So, but in a way, we've come to a roadblock because the activated sludge is quite complicated. It's very sensitive to conditions of temperature, of toxic shock, and so on. And really, there's not much we can do with that. I mean, we can try to use some kind of genetic modification, I don't know, to make superbugs that live forever, but that could be quite dangerous. On the other hand, the reality is that they are very, very sensitive to conditions, and it's a kind of wild animal that you can't really tame. But what we can try to do, I think, is to combine that technology with other things, physical and chemical technologies, because precisely those types of technologies are much easier to control. So you have a coagulation or flocculation technology I explained this morning. What you see is what you get. If you can control the conditions in a precise way, you know exactly what's going to happen. And that gives you a lot more predictability. It gives you a lot more certainty in the design and operation of the system. But I think the challenge remains in one of how we can combine them into a hybrid system. And there is a growing interest now, I think, in the use, for instance, of membrane technologies and coagulation technologies as physical chemical technologies that are being used in front of some kind of bioprocess. And some of the large membrane companies, I think Kubota in Japan and Koch and so on, have already done quite a lot of work in this. There are some very large MBR plants now in countries like Malaysia and Singapore, where this is being run on a very large scale. And I believe that these combinations have a very strong potential to improve the water recovery. But I think that what we can do scientifically may be more limited. And I'm afraid that water treatment is not an exact science. It's a technology, it's an engineering, which means that it's an approximate job. But if it works, that's the main thing. I think one of the other interesting issues that Eduardo and I was discussing this morning was scale up. So things that you can do on a laboratory scale stage, they work quite easily, precisely because you can control the conditions. But you try to build a large-scale pilot plant or even a full-scale system, it's a lot more difficult. There are very serious practical problems that you have to think about when you're building at a large scale. So I think how do we achieve this? We need to work with industry, because the industry will tell you what the practical, real problems are. And you'll never know that if you're working in the lab. What you'll solve in the lab are the fundamental science problems, which is what we need at the start. It's what we need as a basis for design. But to take that to the next level and build it up to a big system needs a lot of money, it needs a lot of resources, it needs a lot of input from other people. So I think they are serious challenges, but they are very interesting ones too. And I believe this can be part of our future. Mario and I were talking about working with companies in Brazil. There's an interest now in wastewater and desalination, and we're hoping that we can attract some funding, maybe to fund DPhils who would like to come to Oxford and work with me on some of these technologies. So I hope I've answered the question.
Yes, and one thing I can just say, it's quite fun to work in Oxford. Besides the work itself, it's an interesting historical place with hundreds and hundreds of years of history in science, so we learn a lot.
We always make a joke with Americans when Americans come to Britain. The joke is that in England, 100 miles is 100 kilometers is a very long way, but in America, 100 years is a very long time.
Yes, Nick, thank you for your very interesting speech, especially in March, April this year, Brazil launched the National Plan of Water Security, and means how can we handle with hazards and risks, not only for the extraction of water, but also dealing with wastewater and with poor and vulnerable communities. So we have a new color maps of different parts of Brazil relating to water security. And the wastewater in Brazil is a big problem because the collecting network of wastewater and the efficiency, or the medium efficiency we are treating about 12% of all wastewater. So our tipping bucket at this point is how can we deal for the next 10 or 20 years facing these problems. And this is also a big bill to be paid for the society. So you mentioned science, you mentioned networking, you mentioned research, of course technology and science. So my question is, how can the United Kingdom is being prepared to face these problems? Because in the national border, they have another situation. But trying to deal with these scientific challenges with overseas countries. Because Brazil has the technology, has the scholars, has the early career students, but still we need to treat more 87% of our wastewater. So how is your picture about this future? United Kingdom with the technology and the science, Brazil with the technology and the science, but with bad figures. What is the approach for that?
Well, that's a very interesting and wide-ranging question. I think let me say one thing. I think when we talk about water, water's not an infinite resource, and I think we all have to get smart with water. We create huge amounts of wastewater in Brazil. It's thrown into the environment, and that's bad for two reasons. One is because that wastewater has a very negative effect on the environment through the effect on wildlife and the rivers and so on. But also it's a shame because it's a lost opportunity. There are resources in that wastewater that could be recovered, that could be extremely valuable. You know, and why doesn't it happen in Brazil? You have the knowledge, you have the technology, you even have the resources in a certain kind of way, but do you have the will? Is it the government and the politicians and the people who drive behind that? In England, we've been worried about wastewater for 200 years. In the 19th century, there were regular endemics of cholera and typhoid in London because the wastewater wasn't being treated, and they had to bring in specific legislation, the Poor Law, various other laws. I have a cartoon somewhere which shows the Houses of Parliament in London, which are right next to the River Thames, and the politicians are unable to go outside on the balcony because it smells so badly. But there were regularly people dying. And so what was done in London, I think, was to introduce legislation which led to the cleanup of wastewater and the banning of the dumping of water into the rivers. All of these kind of key things which were done through law and through politics. And once that happened, it was easier for water companies to then come in and profitably solve those problems because they had to. So in a way, you created an own industry by trying to do this. But that's good because then you're cleaning the environment, you're bringing benefit to the society. So I would say that Brazil can do it, but you need the will and you need the power. You know, but we have to push and push to make that happen. But I dream of the day where you can do that, because I think that would have a huge benefit here and in other countries. I think in the UK we probably treat 95% of our wastewater. Well, we're a tiny country. We can't afford to throw it into our backyard. I think you have, I was going to say you have that luxury, but really you don't. That's what happens, but it's something you shouldn't do. And there must be areas which are being damaged because of that. I mean, we know about the disaster in Minas Gerais with the red mud and all this kind of stuff. So you can't afford to do that, and in future years you're going to pay a price for it. So you have to start now.
And about exchange and research, because all people here are young researchers, early careers, PhD, master candidates. What are the opportunities from Oxford to maintain this exchange and this cooperation alive, receiving PhD or even early career students? The doors are open, the opportunities are big, or with this situation, especially in this moment of Brexit, you think it's perhaps a special moment to reflection?
Yeah, unfortunately I have to say that Brexit at the moment is creating a huge amount of uncertainty in the UK. We don't seem to know what's going to happen, and it's, again, because the politicians can't make up their own minds. The people voted for something and the politicians are unable to make it happen, and so we don't know even where our research funding is coming from. I don't know if I can travel to Europe next month. I don't know if I can go home, actually. Maybe they won't let me home now, etc. So yes, Brexit causes a lot of problems. But in terms of opportunities, I mean, in this kind of area, obviously, I have a small research group. There's René, there's other people. But I would say that with Oxford, it's based on merit. So you would be accepted into a program based on your ability. If you have a very good academic record, you have a GPA here, right? You have that system. And particularly, you have very, very good letters from your professors. So if your professors say that you're the next Einstein, then I think you're in a good shape, or even less, you know. So the application is very important. And if you're really good, you might be able to get a scholarship, but I think maybe better for you to try with the Brazilian funding agencies, because they would love to have top scholars educated in Oxford coming back to contribute to exactly the problems we talked about. You need more people doing the job, that's the thing. You need trained people. So this is the challenge for the young generation to get your training and do that.
The solution is here.
Solutions in front of us, yeah, it's you. We're the old guard, we're moving on, but it's up to you now.
Well, another thing that it worked with us is this more or less short-term internships in Oxford. And I sent 3 students over there, 2 to work with René, 1 with Dr. Hankins. So this is another kind of opportunity that we may pursue. And one thing that we hope that in the near future we will receive people from Oxford here also, because you know, the expertise and some facilities that we have for research on the bio side of the treatment. So, you know, it's important now to couple, and this is one of the things that we want to pursue with the visit of Professor Hankins next semester, is this coupling of research, joint research, real joint research, doing part here, part there, part there, part here, you know, this exchange.
Yes, and one of the, I was explaining to Eduardo that we're sort of 21st century university occupying 12th century buildings. So we have limited space and limited ability to expand, so which I find to be a limit sometimes. So that's one disadvantage to being a medieval university.
But that's part of the fun, and that's why
part of the
you
fun,
should.
though.
Yes, that's part. Well, I can tell you, I think that I spent a night where Sir Isaac Newton also spent some nights. So it's fun, you know. You can look at the walls and say, well, all these ghosts are here, Darwin and Newton and all these big names.
A reminder, Professor Hankins will be staying here until Friday. Tomorrow we have lectures, normal lectures. Wednesday vacations, no lectures. On Thursday we will attend some interested students to discuss, or even some meetings about research. And on Friday morning we have a workshop relating the water, health, and resilience nexus, also with other institutions from Brazil and also from the United Kingdom, also from the United States, visiting us. On Thursday evening, we have also an open lecture from the professor of University of Texas at 5 p.m. also, related to some low-impact development practices. And that is very good to say that this is part of the School of Advanced Studies, and also people are assisting us through YouTube and watching the streaming. So if you have some questions or suggestions, you can address the question to Marina. This is our manager for this module, this block, to myself, or even to Professor Hankins or Professor Eduardo Cleto Pires. We will be very, very proud to help you and to contribute to your better, I say, livability related to these lectures. Last but not least, I have an invitation. We like to take a picture of the first day of the lectures of Professor Nick Hankins. So we are going to be in the line here in front, Professor Hankins in the front, and all the attendees all together around him. So nós estamos convidando a todos virem para aqui para frente e tirarmos uma foto desse primeiro dia. A todos, muito obrigado pela presença, e continuamos amanhã. Muito obrigado, Nick, pela excelente apresentação, e continuemos assim, motivados. Parabéns.